This topic discusses gas-vapor mixtures and their application in air conditioning systems, which are essential in thermal engineering. The main focus is how moist air is analyzed using thermodynamic concepts. This topic forms the foundation for understanding cooling, heating, humidifying, and dehumidifying processes. These concepts are also highly relevant to HVAC systems in buildings and industry.
Lesson Plan Thermodynamics 2. This lesson plan shows that gas-vapor mixtures are part of a larger thermodynamic sequence. Previously, power cycles and refrigeration cycles were discussed as foundations. Then, students moved to gas mixtures, and finally to gas-vapor mixtures. This sequence shows a logical flow from energy conversion to air conditioning applications. Learning Outcome. The learning outcomes emphasize both conceptual understanding and calculation skills related to atmospheric air. Students are expected to differentiate between dry air and atmospheric air. They should also be able to calculate humidity, dew point, and use the psychrometric chart. All these skills are required to analyze processes in air conditioning systems. Specific heat capacity of dry air varies slightly with temperature, but can be treated as constant over a certain range. For temperatures from -10 degrees Celsius to 50 degrees Celsius, Cp can be taken as about 1.005 kilojoules per kilogram degree Celsius. This approximation is very practical for engineering calculations. The resulting error is very small, less than 0.2%. TS diagram and constant enthalpy lines. The TS diagram shows the relationship between temperature and entropy with lines of constant enthalpy. Below 50 degrees Celsius, the constant enthalpy lines almost coincide with constant temperature lines for superheated water vapor. This simplifies the analysis of processes involving water vapor. With this approximation, calculations become faster and more efficient. Accurate enthalpy comparison for water vapor enthalpy values from tables and from the equation shows very small differences. This proves that the approximate equation is sufficiently accurate in the range from -10 degrees Celsius to 50 degrees Celsius. Therefore, the equation can be used for quick calculations without significant loss of accuracy. This approach is very useful in moist air analysis. The comparison of water vapor enthalpy values shows that the equation provides accurate results with negligible error. Vapor pressure of saturated air. At 25 degrees Celsius and 100 kilopascals, the saturation pressure of water vapor has a specific value that defines the saturated condition. If the vapor pressure is 0, the air is called dry air. If the vapor pressure is less than the saturation pressure, the air is unsaturated. If the vapor pressure equals the saturation pressure, the air is in the saturated state. Specific and relative humidity example. This example shows the difference between specific humidity and relative humidity. Specific humidity represents the mass of water vapor per unit mass of dry air. Relative humidity indicates how close the air is to the saturated condition. In this example, the air contains only half of its maximum moisture capacity. Moist air enthalpy and mass. Moist air is treated as a mixture of 1 kilogram of dry air and omega kilograms of water vapor. The total enthalpy of this mixture is expressed per kilogram of dry air using H equals HA plus omega Hg in plain text form. This approach simplifies energy analysis in air conditioning systems. The total mass of moist air becomes 1 plus omega kilograms. Constant pressure cooling and dew point temperature. This process shows the cooling of moist air at constant pressure from one state to another. The cooling continues until the temperature reaches the dew point temperature. At this point, water vapor starts to condense into liquid. The TS diagram is used to illustrate this process conceptually. During constant pressure cooling, moist air is cooled until the temperature reaches the dew point, TDP, where condensation begins. Condensation on cold drinks, the sweating effect. The sweating effect on a cold drink can occurs because the surface temperature is below the dew point of the surrounding air. The moist air near the can cools down, and its water vapor condenses. The water droplets on the surface come from the air, not from inside the can. This example connects theory with everyday experience. Adiabatic saturation process. In this process, unsaturated air enters and leaves in a saturated condition. During the process, there is no heat transfer to the surroundings, so it is called adiabatic. The air temperature decreases until it reaches the adiabatic saturation temperature. The TS diagram shows the path of cooling and humidification. Wet bulb thermometer. A wet bulb thermometer is made by wrapping the thermometer bulb with a wet wick. When air flows over the wet wick, evaporation occurs. This evaporation absorbs heat and lowers the measured temperature. This temperature is directly related to the humidity level of the air. Sling psychrometer. A sling psychrometer consists of a dry bulb and a wet bulb thermometer. The device is swung in the air to ensure sufficient airflow over both thermometers. The difference between their readings is used to determine the air humidity condition. This method is simple but very effective in practice.
Answer B. To determine the difference between wet bulb and dry bulb temperatures for humidity calculation. Explanation of why other answers are wrong. A. To measure air pressure and altitude. Incorrect, because a sling psychrometer measures temperature differences, not air pressure or altitude. C. To measure wind speed and air velocity. Incorrect, because the sling psychrometer is designed for temperature readings, not wind speed measurements. D. To record temperature changes over time. Incorrect, because the device does not continuously record temperature changes. It measures wet bulb and dry bulb temperatures at specific moments.
Psychrometric chart. The psychrometric chart shows the relationships between dry bulb temperature, specific humidity, and other moist air properties. It contains lines of constant wet bulb temperature, constant enthalpy, and saturation. This chart is the main tool for air conditioning analysis. With this chart, many air properties can be determined without lengthy calculations. Saturated air condition. For saturated air, the dry bulb, wet bulb, and dew point temperatures have the same value. This condition is represented by a single point on the saturation line in the psychrometric chart. The example at 15 degrees Celsius shows all three temperatures coincide. This condition simplifies analysis because there is no uncertainty about moisture content. Air conditioning. Although we cannot control the weather outside, indoor conditions can be controlled. Air conditioning allows the adjustment of temperature and humidity to meet comfort requirements. This concept is very important for buildings, offices, and industrial facilities. With HVAC systems, indoor environments can be made stable and comfortable. Indoor climate control. Comfort beyond outdoor weather. This concept emphasizes that indoor thermal comfort can be controlled regardless of outdoor weather conditions. Air conditioning systems regulate temperature, humidity, and airflow to suit human needs. The human body also generates heat, so the environment must be controlled to maintain balance. This illustration shows the importance of indoor climate control in enclosed spaces. Air conditioning processes. In air conditioning systems, there are four main processes: cooling, heating, humidifying, and dehumidifying. These processes can occur separately or be combined as needed. Examples include cooling and dehumidifying, or heating and humidifying. All these processes aim to adjust air conditions to achieve comfort. Air conditioning involves four main processes: cooling, heating, humidifying, and dehumidifying. Air heating, constant specific humidity. In air heating, the air passes over heating coils and its temperature increases. During this process, the amount of water vapor per kilogram of dry air remains constant. However, the relative humidity decreases because the air's capacity to hold moisture increases. This process is common in space heating systems. Air cooling, rising relative humidity. In cooling without condensation, the air is cooled while its moisture content remains the same. When the temperature decreases, the relative humidity increases. This example shows a change from about 30% to 80%. This explains why air feels more humid at lower temperatures. Heating and humidification process. This process consists of two stages: heating and then humidification. In the heating stage, the temperature increases while the specific humidity remains constant. After that, the air passes through a humidifier, and its moisture content increases. The final result is air that is warmer and more humid. Evaporative cooling in porous jugs. Cooling occurs because water seeps through the porous wall of the jug and evaporates at the surface. This evaporation process absorbs heat from the water inside the jug. As a result, the temperature of the water inside becomes lower. This method is very effective in hot and dry regions. Evaporative cooling of air. In this process, hot and dry air flows over water and becomes cooler and more humid. During this process, the wet bulb temperature and the enthalpy remain approximately constant. Cooling occurs without adding external energy. This principle is widely used in evaporative coolers in dry climates. Answer B. Enthalpy and wet bulb temperature. Explanation of why other answers are wrong. A. Dry bulb temperature and specific humidity. Incorrect, because the dry bulb temperature decreases while specific humidity increases during evaporative cooling. C. Relative humidity and dew point temperature. Incorrect, because relative humidity increases and dew point temperature changes as air becomes more humid. D. Dry bulb temperature and enthalpy. Incorrect, because while the enthalpy remains roughly constant, the dry bulb temperature decreases, not remaining constant. Adiabatic mixing of air streams. Two air streams with different conditions can be mixed without heat transfer to the surroundings. The final mixed state lies on a straight line connecting the two initial states on the psychrometric chart. The enthalpy and specific humidity of the mixture are weighted averages of the two inlet streams. This process often occurs in ventilation and air conditioning systems. Counterflow cooling tower. In this system, warm water enters from the top and flows downward, while air flows upward. This counterflow contact increases the effectiveness of heat and mass transfer. Part of the water evaporates and absorbs heat from the remaining water. The cooled water leaves at the bottom to be reused. Natural draft cooling towers. These cooling towers use natural airflow without fans. The tower shape is designed to create a chimney effect so that warm air rises naturally. Cool air enters from the bottom and warm air exits from the top. This design is efficient for large-scale industrial applications. Spray pond cooling. In this system, hot water is sprayed into the air to increase the surface area of contact. With a large surface area, heat is released more quickly to the environment. Cooling occurs mainly due to evaporation and convection. This method is often used when large land areas are available. Cooling pond. A cooling pond works by allowing hot water to spread over a large surface and release heat to the air. The cooling process occurs naturally through convection and evaporation. This system is simple but requires a large area. Warning signs indicate that the incoming water is still at a high temperature.
A cooling pond dissipates heat from water by exposing it to the open air. References. All figures and concepts are taken from a standard thermodynamics textbook. This is important to maintain consistency and accuracy of the material. The reference can also be used by students for deeper study. This book is one of the standard references in engineering thermodynamics.